I noticed when you do the design of that, it's a mixture of both rotary actuators and linear. And like all your other bots are all rotary actuators. And so suddenly now you're developing linear actuators. So that means you must have a lot of in-house talent to suddenly say, all right, we think that there's some actuation strategies here that are going to be different on the humanoid, and being able to build that. Is there anything that you would like to address in kind of going on that route?
Hmm. So I actually saw the video of you like talking about all the let's say technologies we built in, and yes, I can tease here. Also, the newest generation for anyone, it's uh, we had again changes in there to like we changed some of the actuators, let's say back to, linear actuators back to rotary. But in the version like the Gen 2, basically we trying to get as compact as possible and as much power out as
Yeah.
possible. And we couldn't, like, even we designed the actuators ourselves, we couldn't design a rotary actuator in the same, let's say, in the size to still let it look sexy, let's say, like that,
Yeah.
and have let's say enough power. So the power density was still a little
Yeah.
issue, and this one we improved a lot. So we have like, right, like before, let's say you had like 150 newton meter or whatever. Like now our newest actuator, like in the same, like, even we always, let's say, calculate the weight to the power density, or like the power, like the power of it. So and this time we reach about more than 300 in the same size.
Wow.
And so it is, I would say, one of the most powerful actuators we now will present, like with the newest version. And we actually found, while like now building them already and testing and whatever, and the beauty of making your own actuators and having your, like, a very smart team around it, which is growing like with every step we are doing. And so this, but also for the linear actuator, they were actually pretty simple to build, because it's nothing else than a rotary which has like just something inside which is turning, instead of you're using like with
Yeah.
an hollow shaft, like. So yeah. And but we changed a little bit. We still have some linear ones, but actually also there where we
Yeah.
need again a lot of power
And
and to
compactness, because
and
your
compact.
your wrist is, because when I was first looking at the wrist, I'm like, wait a minute, I don't see it. That's such a slender list. There's no way it moves in all directions. I had to get in really, really close to see how you
Mhm,
did it. So that is the most compact, sleek wrist I have ever seen. And
mhm.
I think there's also some very good design decisions on you looking at the range of motion and actually having a non-symmetric range of motion, because my hand can only go up so far this way, but it goes a lot further down that way.
Yeah.
And I noticed that you designed it the same way. And because of that, you were able to change the constraints on it so that, yeah, you can get that full movement in there. I wasn't sure you could get that. And then, like, sure enough, it's in there as well. So,
It is.
so
Yeah.
it's like, it is one of the most impressive ones. Now, one thing that I have to check on is that I think it was because there was a computer graphic image that was a head turner for me. Is I looked at it, it looked like you had like a rotation below the knee. I don't think you do on the actual
Oh,
one, but it was kind of suggestive in that, and that's what they, okay, I got to look at this and find out what's going on, because it, no one has any rotation underneath the knee. And
uh-huh.
of course your ankle joint is basically kind of like the wrist joint, which again
Exactly.
makes sense to some everyone. If they're not using a linear actuator, they're using a rotary actuator to do the same thing. No one's really built them right in to the
Yeah.
ankle itself because it's too big. So that's pretty
We
interesting.
So on the ankle, we also do have like two actuators, like the wrist, like here
Yeah.
on the hand, or so, and you have like a middle point, and then you have two actuators where can just go in all sides, or like we do, but it's kind of limited in one direction.
Yes,
So
exactly. And
and
same with the human hand, is that you can only do so
yeah,
much this way, but you get a
exactly,
lot that way. And that mechanism works the exact same way, which is why it's a
exactly.
perfect choice.
Yeah.
The other choice, question I have about for anyone, is I notice it seems to be a lot taller than the other offerings that are out there. And is there any reason why you chose a particular height?
Yeah. I think that's probably, I just want to have someone like the same height as me as me.
Yeah.
And so it's a little smaller than me, so it's one like in centimeters, like 180,
Yeah.
and so I'm 183, so it's fine. But it's, I would say it's more. probably just try to do like build one like in a size of let's say the average in Germany. I would say that
That's what
was
I
the main.
assumed. It was, oh, it's a German demographic. That's the 50 percentile in Germany. Yeah.
Hi, I'm for anyone. I can do more than you think. Scan completed. And you, what do you want me to do?
Okay, so Mara, we have the pleasure of being joined with David, the CEO of Neura, and one of the new bots that we sort of evaluated a few weeks ago. And I had to apologize on that because you guys have been on the market for a while with a lot of very interesting things. And now that I took a look, wow, you've come a long way. So I have a lot of questions I'd like to pose to David about the evolution of Neura, what your overall strategy is. Certainly, we're interested in humanoid bots, which is one of the angles that we come from. Uh, but your company is a lot older than it's not a startup, okay? That's for sure. But it's a young company. And for those who remember, it was like 2019. That's pre-COVID, okay? So most of the humanoid bot companies are kind of post-COVID going on in there, and you already have a track record. And you didn't start with humanoids at first. You started with what everyone would say were traditional kind of robotics. So you have cobots, you've got mobile industrial robots that are out there. And back in 2019, what did what made you think that you could come into this market that already had plenty of incumbents and in some way disrupt it or provide some value that was missing? That's sort of the first question I have. And then the second is, was the humanoid form or human scale already on your roadmap at that time?
Mhm. So thanks for the questions. I really like them. So um, yeah, 2019. The main reason for starting Neura Robotics was to make robots cognitive. So there's also like we started on the first of May in 2019 with a team of, let's say, friends, and we were 12. So the best engineers I actually know, like for SAF or AI, hardware development, sensor development, and the main reason, like I also when I introduced the project to my team, so we're sitting there. I had a wall of friends, I always call. So every robot company which is existing on the planet and all the core products they have on a wall. This wall is still existing, and so I showed the team like it does not make sense to build another robot because there is already enough, and they're all competing against each other. So the idea was, let's say, and there was a picture above of that, making robots cognitive. So it means give them the ability to hear, to see, to feel, the feel of touch, and put and distribute, let's say, the brain and in different levels to make actually physical AI. Today it's a buzzword. Like today, everyone knows what I'm talking about. Maybe not precise, but still. And this is actually what we started. We started with making, let's say, building a platform which enables physical AI and gets the right data streamed, so it can actually react fully autonomously. And where does it come from? So before I started Neura, I was actually building three other companies, and they were all in the space of robotics and also automation. And during the time of automation, I figured out that it was still super complicated and way too complicated to bring this robot into the field, and even my own robots. So, and that made me worry. So I thought, okay, I had like an amazing project. So I will not call the name of the company yet, but so I started. So the first decision was I only take projects where I have more than one machine. So more than one application, the same application, or so. And one of the project was like 14 machines, so for 14 bin picking applications, but completely the same. And I sold them with a lot of happiness because I really thought, okay, the first time I really earned money when in the end I did not. So and this is where I figured out the issue was that I was actually seeing the robot just as a piece of metal with motors, and I had to somehow add the whole periphery. And then I had to have, like, I always had like this amazing smart people which put all of them together. And so the most difficult part was when something changed. So it means what it changed, mostly like the light conditions, the maybe the part a little bit or whatever, and I had to rebuild and reinvent the wheel every time. So, and the basic idea of me was, why don't I put all the sensors inside the robot arm and create like a platform, something which can further develop, and not just by ourselves, but actually that the community can actually contribute, and everyone can actually further develop instead of redevelop and reinvent the wheel. And that is actually where Neura comes from, and the name also comes from more. I'm talking about neurons, like it's more about perceiving environment and being able to react on it, and yeah, that's like, let's say, overall.
Okay, and the Neu in Neura also means new in German, so I wasn't sure if it was like somehow a mashup of Neu and robotics and something else, but it's a definitely a new paradigm, in that everyone thinks of, like you say, robots as hardware, but they forget that the real power of the robots is the fact that they're reprogrammable. Because we have plenty of machines out there that can do all sorts of things just as fast as robots, sometimes much, much better, but they're just too specialized. It was always about the reprogrammability. And ironically, that's been the hardest part of it, because everyone thinks it's hard to build hardware. It's like, yeah, it is hard to build hardware. Turns out it's a little bit harder. And I come from that very old school background of trying to solve that problem. And that's been something that's been nagging me for 40 years. Is like, there's got to be an easier way. Why can't we just tell it? So when I'm starting to see this kind of approach, I just stand up and applaud, because it's like, yes, finally everyone gets it, that that's a way to do it. And it takes kind of like a new generation of people that have been exposed to these different ways, and also the difficulty of being able to program that. So you're getting this data.
Mm-hmm.
Obviously, you've shipped product. Neura has several
Mm-hmm.
robots right now. Um, it seems to me you're getting a little bit more than just the the data of how the robots will function and training them on that. You're also getting user requirements, aren't you? So you're already in the factory. You're already seeing what the automation difficulties are, and you're seeing how this ecosystem, because that's what you really got. You've got a rather interesting ecosystem in which you've decided to now put in some human scale bots. And when I say human scale, I mean there are some bots that are not quite humanoid in form, but are able to operate in a human environment and provide utility there. What sort of caused you to make the pivot into that? And was it new opportunities, or did you just see it as like one more important piece of that ecosystem?
Mm-hmm. So yeah, actually, we never had really a pivot. It's more a further development. Or so, I think that the first difficult thing is like starting this kind of company at the time of 2019. Let's say a full stack company, not the hardware, not a software, not an AI, but actually all of them, out of Germany. So that's already one crazy thing, because it makes no sense. So Germany, the things are different in one way, that still very the, let's say, definition of a vision is still a little different. Like in US, like you have a definition like of vision is like something which could be someday, and in Germany it's like it will be one day. So and the thing is, but it's actually, let's say, it could. So when I started, I was talking about robots which you can simply interact with in a natural way, like with a human. So it means you simply talking to the robot, tell the robot what to do, and the robot will understand that, and you will not have any requirements of programming in it. So that was the basic vision, and nobody, like in the beginning, nobody believed it. So my idea was, then I just built a much better, let's say, hardware and software, just in the basic, let's say, performance pillars, like
Mhm.
performance, like in speed, in accuracies, and sensitivity. And that's how I get this robot into the market, because this is something everyone understands. And then further, place also the compute on the right sides to actually be prepared for the further step, which is actually bringing all the cognitive abilities into the robots. And this is still the thing we are doing. So if you look also into our products, the first robots we launched, we were faster. We were more than 4 times faster than the fastest cobot on the market. So if you look at our accuracies, we were more than 10 times more accurate than any others, and we are still the most accurate device on the planet. So like the whole, let's say, secondary encoder thing and whatever, it comes actually from us, because it's a longer story. So then there, like, also sensitivity. So we invented like a new full stock sensor to actually not pay like 10K for a full stock sensor and then having like a lot of noise in the full stock sensor, whatever. And you probably know all the suppliers there, but we actually invented one which you can really afford, and it has a very high robustness. So that was also the first focus. And after founding the company, and I can still show you there, we actually let's say we took exactly 7 months for that. So we reinvented even the whole sensors. So it means like encoder technologies to make like a dual encoder inside with the highest, let's say, resolutions, like 25 bits on the output side, so on the load side. And then having, for example, own full stock sensor inside, and also all the cognitive abilities on that. And it's not enough, but this is something I think it will probably confuse everyone if I go like into every details. But there was much more to reach. For example, just the accuracy part. It was not just the encoder. It was actually much more. We even had to reinvent the whole structure to develop a structure which was not like by temperature change, not going in all directions, because the mathematics behind would be way too complicated. So you need like a Siemens 840D controller to somehow have enough capacity or enough compute to realize that. So we made actually a software-defined hardware to reduce the compute, to change, like to do it like directly on the motor side, like having already a controller and still reaching, let's say, the highest accuracies. It was like a lot of topics inside, but in my opinion was just like, I think every engineer will love it if I really go into detail. Because there was a lot of details, but we changed a lot of things in the first where everyone can understand. And in a second, we were working also in parallel already to make actually the next big step, because I do believe that just making a robot faster or whatever is not really, let's say, sustainable, or because everyone will, till you reach the market, others are also in the same. And that's also what happened. And but the big sustainable part was building a robot which is designed for a platform to be further developed, where we actually knew our biggest weak point is actually ourselves, the limit of ourselves, and we need to enable others to work on our platform to get us, let's say, on speed, like what Steve Jobs did with the smartphone. And like this is pretty much the concept behind everything and what we started from the first day, and we are still working on it.
Okay, so it sounds like you are building your own actuators. Is that correct? Or at least you've designed them.
Yeah.
Are you also manufacturing them?
Yes, even their own motors, own encoders, own brakes, own like
Everything.
We go like super deep.
Nothing's coming out. So you have that, and these are basically cobotic actuators. Cobots have to operate, because they're called cobots. They're collaborative around humans. They have to be safe. That means when you start to pivot into humanoids, you've already got a lot of safety protocols under your belt. You know, a lot of what's going on. You've already got the hardware. I assume what's going into your humanoids is very similar, if not identical hardware that's on there. So it's not really a pivot, is it? It's just like it's a continued evolution marching on down there, because you've already demonstrated this hardware works.
Yeah, exactly. So what do I see if I look at a humanoid? I see 2 arms on a less stable platform. That's basically what I see when I look at a humanoid, because the main work is always mostly done like with the hands and the arms, and they are, let's say, the core value bringing components are. So and you're right. This is also why, let's say, it's always a further development. Like everything we did was like the actuators and whatever. So there were still, for sure, further developments, like to get more torque out, to get less space, get more compact. And there's still a lot of things we're working on even, and to get even better than what we have today. But the whole part of safety is, I think, a very important part. So myself, I'm also a safety engineer. So I'm let's say everything we build is redundant, diverse. So to reach the highest performance level, like we always talk about CL3 or PLE, and this is actually also like even the actuator itself, it's already safe. And then we are having like also, let's say, the cartation safety. I think you know probably what I'm talking about. Like every robot arm, it's not enough to have just safe access, but you even, let's say, to sell it, it could be, but the integrator will have the issue later. So we do have also to implement cartation safety. So you need, like, for example, and safety controller where you can do like all the safe multiplication of access and to get like safe speed, safe torques on forces on a TCP. And these are things which we solved many times in all the robot, let's say, arms we built until today, and also the mobile vehicles. So there's all about moving safely in the environment. And what we have in the humanoid is nothing else than combining all of them again and adding two major things which are still, let's say, parts which are not defined by norms or anything, but it's like the falling behavior of a humanoid, for example. These are things which we have a solution, but let's say I will probably not go too deep into that right now because it's at this time we first want to present it to the market, and then we will probably talk also deeper about it.
Right. And that's, I think, a very important area that's going to be evolving quickly is the safety standards. So no humanoid bot is certified safe yet. And the reason is because there is no certification that they can be certified
Exactly.
to. So you're kind of working, and I assume you're part of one of those committees or starting one of those. I think there is already an organization in place that is
Yes,
looking at
there is.
that. And is it like maybe 12 months away or so
Mhm.
from there actually being a standard?
We are also involved into some of this new standards. Let's say building the new standards, and in the same time, like we like let's say like that, we are also involved to even find new solutions for that. And I think one of our core, let's say, products for that, and this is something I can talk about. It's like, for example, our SHD sensor, so a safe human detection sensor, which we invented. So this one we invented also not just for humanoid, but any kind of technology of robots, because simply until now, even if you are talking about collaborative robot, it's not really collaborative. It's just collaborate. I always say like it's more collaborative that you can really finally use it like easier to use than a standard industrial robot. But if you're looking for a real collaboration, then you will still, like, if you're applying all the norms, it will be super tough because
Yes.
basically you're required to do risk assignment in the end of before you're using it, and this will give you a lot of pains because you will not be allowed to use certain radius of components and whatever, and this is pretty unrealistic for the real world. So what we did, so I never believed in the really like colliding with something and then knowing there's something and stopping, but not knowing what it is, and then just for the somehow somebody has to reset and just let it run again. This is like the standard way of everyone doing it until today. What we believed in always from the first day was like non-touching safety technologies. So it means like already it's a human, and then before you're touching, you're just stopping, and if the human is like going out of the way, you just continue, because the robot is, let's say, or the sensor is safe and can identify human from other objects. That is something we also invented in the time. So we presented already. We did also present it on the Automate last year, I think, in US, and we will also show now a newest generation of it on a 24th of June on the Automatica again. That's a sensor which I would say it will change the world in robotics completely, because you finally are not guessing is a human or not, and is another robot or whatever. This super big complication in the world, and we solved that with a new sensor technology.
Yeah, that's going to be important for cobotics because uh, what some of the audience may not quite understand about the cobots. They say collaborative, but you're right. It's not like it's really handing things off and you're shaking hands and stuff like that. It just means you can be around it or close by, and you don't have to have all the safety protocols in place you would for a big IR robot, meaning like screen having fencing and everything else. But you need a sensor to know when a human is nearby, so the robot slows down. So the robot does hit you, it hits you at a slow enough speed, and it's round enough, and it's soft enough, and compliant enough that it's not going to do more than a little bit of bruising. Hopefully not more than that, and hopefully not even that. And then when the human's out there, suddenly it can go about its business a little bit faster. So that's clearly going to be very important for humanoids, since it'd be very near. Now, the one of the human scale bots you have, I think it's Mira or MIPA. I've seen that from your webpage that it seems to be in like hospital settings, in healthcare settings. The standards there must be something else, especially for safety and sanitation and everything else. So that's also a bit crazy. But at the same
Mhm.
time, it gives you insight on what you would need for a humanoid, correct?
Mhm. So yeah, so there is actually, just to go back on the let's say risk assignment, whatever. There's like the 15066, which calls actually how much pressure you're allowed to put on what kind of part of your body, and it's like very clearly defined. And the the most difficult thing on that is like a human is like not just staying in one position and whatever. So it's like the risk assignment is just to somehow get them into the market, but there's no clear, let's say, really like, yeah, you need to be careful anyway. So, and that's the part on that. And if you solve that, like with the safe human detection sensor, you will have this piece out of your mind that will never happen anything, because you know the robot will never touch a human if the human don't wants it. And then coming to the other environments, the fun part on it is it's actually more difficult to get a robot, let's say, running in the industrial settings safely than into homes. There's a completely different norm appliance like on
Yeah.
that,
Okay.
because the part of like, because the responsibility in every factory is actually still by the let's say company owner, or the managing director of the company. So, and this is also why they're much tougher, because you somehow have to, let's say, secure or like ensure the safety for every like employee you have in your company. And it's also right to not put them into dangerous situation. That's also why this one is much tougher. It's like more tougher than autonomous driving. And then like from the norms, I mean, you cannot apply machine learning, for example, into because it will know room, because it will always have, like for a reaching PLE, for example, you need redundant and diverse. And if you're talking about machine learning algorithms, like you never reach even 100%. And in the norms, you will need to have 100% for both, let's say for two ways of it,
Hmm.
to identify a human, for example. It's very tough. And that's also why there's no other sensor existing except ours in that segment right now. So, and then let's say for different environments, it will be also, let's say, one is like interacting with a human in a safe way, and then in the most logic way. Also, if you're talking about humanoids, you will have like an additional thing. It's about the falling, which is still, let's say, a very very tough thing where everyone needs to have a solution for.
Yes. Yeah. And that's going to be tricky. I've had my thoughts that, the boss just have to figure out how to fall gracefully. I use the example, if you go to a climbing gym, before they let you climb there, you have to show that you can fall
Yeah,
without
true.
hurting yourself. So, and there's certain ways of doing it. So I imagine that that's one of the things that the bots are going to do, rather than just collapsing and going down the floor. They can get into a tuck and roll or do something like that. The other thing is, of course, the material selection that you're using, how things are exposed, how soft everything is. Like you talk about, like the cobotic standards, is robots used to be very square, and
Mhm.
then it turned out that was a bad idea from safety, because corners, when they hit things, they really hurt. So if you start rounding them off, and that's why cobots are very round, you need the same thing
Mhm.
for humanoids. You got to worry about the pinch points and everything else. How do you cover them up? Make sure fingers don't get caught in there. You get a lot of IP standards you got to run through as well. So there are definitely challenges. I thought that like the hospital environment would be like one of the toughest ones, because
Yeah.
man, it's you're in amongst patients. But I guess in some ways it's easier, because like the one question I was going to have, there's probably two questions I have to ask you, because they're the
Mhm.
questions everyone always asks. you're probably sick and tired of this question, but I think they're legitimate questions, and I always like to hear someone's answer first. Is why the humanoid form?
Yeah, that's a good one. I actually like the question because, so at this time, for example, for a household, I would say, uh, why should you now wait for a humanoid form factor and solve all the issues you have? While not you, why don't you use just, let's say, two arms on a more stable platform? This is also why we just launched MIPA, for example, like 2 days ago, and it's on wheels, or it's a smartphone with arms on wheels. That's the definition of it. Or so it's much simpler. It's very stable, safe, next to humans, children's, and this is, let's say, the but in the longer term, I think one form factor will just reduce a lot of cost and a lot of complexity, and you're talking just to one device and everyone has the same or some. And then the biggest, let's say, from industrial perspective, I always ask the same question, because I see like the best floors, I see there's mostly like even elevators having already all the integrated, let's say, sensors also to just communicate with them. So why don't you just use a mobile platform with one or two arms, or 10 arms if you want to? It's much simpler, and then you will actually get also, the main answers for that is, that everything is designed for the form factor of a human, like in the heights and the, like the bottoms, the like everything is just designed for a human. And the whole, let's say, thinking of every company I'm talking to is more, you just leave everything as it is, like all the machines, everything, you don't invest into that. You just simply bring, instead of a human, which you maybe cannot hire because, um, like, nobody wants to work on or whatever, you just simply use their, a humanoid for that. And this is like not so difficult, and I think it makes a lot of sense in that way. And the other big reason, in my opinion, so it's something I always make the example of my mother, that opened my eyes. Like, I build robot, also humanoids, because I really love to do it, because it's super complex, and in the same time it's something I think the world is dreaming of for a long time. But then when I talk to my mother, I realized one thing. So she's asking me about 15 years now what I do for a living, or so somehow, and she's not dement or something. Like, she really tried to understand what I'm doing, and that's already for some time. So she's not like very technical. So she asked me, and then I was always, I do robots, and she gets excited, and she's like, oh wow, awesome, so show me one of your robots. So I show her a video of an arm doing welding, doing whatever, machine tending or whatever, and she will always answer, oh wow, nice, looks complicated. So, but she did not get it, or
Yeah,
so somehow I saw in her eyes, like, okay, well, it's not a robot. She was disappointed, probably because it did not look like Terminator or whatever. So, and and since I shown her a humanoid, she knows exactly what I'm doing. She has a lot of idea what this thing could do for her. And this is, in my opinion, this opened my eyes. This is actually what the world needs. Like, they need to understand that they can actually imagine themselves. Like, yeah, simply, I see the fingers, I see the arms, see the legs, whatever. Yeah, it can do exactly the things we can do. And that's also why I do believe that this form factor will enable robotics a lot to go into all kind of fields. And this is, let's say, the second answer. It makes sense in some ways, not in all. But I think if you have like one form factor and you scale that one, is also from a cost point of view, from many point of views, like, it will be one solution.
yeah,
It's just complex.
yeah, yeah.
that yeah.
And for me, that's a very familiar story, because whenever I told people that I was in robotics, I assumed I was working with C3PO all day, and then I'd show them the arm, and they'd be
Yeah.
like kind of disappointed. The other thing that's, I think, interesting about the scaling, um, one of them would be, is like, is there going to be sort of a standard size that everyone goes around? Because when you build a factory and you have a workstation, in order for it to be ergonomic, it has to work between the 5 and the 95th percentile, which a lot of times means they need to make these tables that are adjustable and everything else for that particular worker that goes in. But if all your workers are the exact same size, and suddenly you don't have that requirement anymore, because it's
Mm.
maybe the 50th percentile humanoid, which matches whatever that population is. That's one way of being able to bring the cost down. The other thing I agree with is that the idea is not to have to completely rebuild the factory for the humanoids to go in. We want it to have a nice direct swap out.
Mm-hmm.
So, part of that then goes to the follow-up question, of course, that you probably hear all the time is like, wheels or legs? And it seems like you've got a combination of both.
Yes, exactly. So at this time, we have I think that's a Neura story. We're, I think, the only company in the world which has all of them. And we really say, like, at this time for us, the form factor does not matter at all. Like, it's we really focus on like what is like the benefit every partner gets, and the main benefits they get is actually from the platform. So we combine every kind of form factor on a Neuroverse platform, which is basically, let's say, a developer environment, a simulation environment, and let's say an app store and a skill store, let's say, like that. And this is basically, let's say, the biggest benefit we get. And the form factor, we will probably, let's say, until a certain, let's say, a time where really the humanoid form factor is just stable enough and good enough to really solve the, let's say, the most of the problems. Until there, I think we will have this discussion which form factor is the right one, because the wheels are just easier. And until there, I think it is required also to have more of them, because if not, you will probably lose also a lot of, let's say, the data, and at the same time a lot of, let's say, of the markets, by simply, let's say, a definition of somebody like is taking, or decision somebody's taking, which form factor is right. So I think the answer was complicated, but it's still, let's say, we believe in all kind of form factor until a certain time, where one form factor like a humanoid will just make sense, will be stable enough, good enough, where everyone just will put everything on that platform. And for us today, it does not matter at all.
Yeah. So if I go back to the ecosystem you have, I think that gives you a distinct advantage. First, you're already shipping product, you've already got revenue, you're already dealing with these different clients to understand their needs. But whenever you go into any industrial setting, it's not just people that are out there. There's all this other equipment that you got to deal with. There's a lot of automation, and all of it has to be tied together somehow with the software. So if you were to say you went into a factory and you had a competitor that had like a humanoid that's absolutely identical to yours in every way, in cost and functionality and stuff like that, I assume you would get a little bit of advantage, because you say, wait, and we already know how to integrate in with all this other equipment you have. You've got industrial robots over there you're going to be working with. You've got mobile robots that are moving around. We've already had to deal with MES systems and everything else. So do you see that? Because to me, it's not going to be just as easy as dropping the robot in there and just assuming he reports to the foreman to say, okay, what am I supposed to do now? But there's going to be this tight integration with software systems. So there's literally, you want all the people out of the loop, including the foreman.
Yeah, I think that's exactly the thing. To bring now, like, it's all about also data, and it's all about like how do you gain the data, and at the same time also how do you find the right structure or architecture of your physical AI to really cover all delays and have the, let's say, the perfect setup, let's say, to make it like really scalable. This is, I think, what we are working mostly on, and we believe we are right now on the time where we think, okay, now it will start to be scalable. So yeah, it's actually what do I want to say? Like, I'm just thinking about. We did not, like, we don't want to wait until the humanoid, like all the issues on a humanoid form factor is solved, until we are actually gaining the right data and using building the right skills, and let's say, and finish the platform for it. The big advantage, we have already thousands of units in the field. We have thousands of units which have cameras, microarrays, force shock sensors inside, which are actually gaining already the right data and have already the compute on the right sides. So we can actually, let's say, finally, let's say, finish the platform and and have already enough data to actually train the actual humanoid without, let's say, dealing with the instability of let's say its legs or whatever. So, and this is basically, and there's much more than legs. There's also the whole upper body and everything you need to stabilize. But the real benefit you get is still in the hands and the arms. So, and there's still the feel of touch and the cameras, which are recognizing things, let's say, and you're building the functionalities around. So for us, it's just the right way. So simple explanation. We are not just waiting until there's flying cars. We actually still build the streets. We are driving on wheels until they are there, and then one day there will be flying cars, but we also cover the whole way there. So
Yeah.
and we leveraged actually the humanoid in the same time. So it's always contributing. Everything we do today is contributing to the right humanoid in the future.
Okay, so I get a couple of, I think, quick questions here that you can
Yeah.
answer. Is that, you announced MIPA I think about a week ago, and so I went to your website, and I see you can already do pre-orders for 100 euros. And so my big question is, do you deliver outside of Germany?
Yes, we will deliver outside of Germany, but at this time, let's say like that, I think the first which are getting it will be close to us.
Okay,
Let's say
it's a good thing
the
I've got a German mother-in-law, so that's why I asked
yeah,
the question.
that's good.
And for those who are wondering, I think what the price is.
Yeah.
What was the price? The final price?
Actually, right now about 10K.
About 10K,
So
10K
yeah,
euros. So it's
yeah,
gonna be a little bit tougher for the Americans right now.
yeah, yeah.
uh,
It's
so
all in Trump's hands.
yeah,
You
exactly.
he can still change his decisions.
Yeah, but I'm just looking at the euro dollar right now. It's like, whoops, it
Yeah,
already is like
exactly.
50% on top.
Yeah,
So okay, so if anyone wants to, they can go ahead and pre-order it. But I guess you have to probably live in Germany or at least the EU. It will be a little
yeah.
bit easier to get. The other question is like your humanoid bot, which is called Für NA Bindestrich 1, or as most people would call for anyone. I noticed when you do the design of that, it's a mixture of both rotary actuators and linear. And like all your other bots are all rotary actuators. And so suddenly now you're developing linear actuators. So that means you must have a lot of in-house talent to suddenly say, all right, we think that there's some actuation strategies here that are going to be different on the humanoid, and being able to build that. Is there anything that you would like to address in kind of going on that route?
Mm-hmm. So I actually saw the video of you like talking about all the let's say technologies we built in, and yes, I can tease here. Also, the newest generation for anyone, it's uh, we had again changes in there. To like we changed some of the actuators, let's say back to linear actuators back to rotary. But in the version like the Gen 2, basically we trying to get as compact as possible and as much power out as
Yeah.
possible. And we couldn't, like, even we designed the actuators ourselves, we couldn't design a rotary actuator in the same, let's say, in the size to still let it look sexy, let's say like that, and have let's say enough power. So the power density was still a little
Yeah.
issue, and this one we improved a lot. So we have like before, let's say you had like 150 newton meter or whatever. Like now our newest actuator, like in the same, like even we always, let's say, calculate the weight to the power density, or like the power, like the power of it. So and this time we reach about more than 300 in the same size. And so it is, I would say, one of the most powerful actuators we now will present, like with the newest version. And we actually found, while like now building them already and testing and whatever, and the beauty of making your own actuators and having your like a very smart team around it, which is growing like with every step we are doing. And so this, but also for the linear actuator, they were actually pretty simple to build, because it's nothing else than a rotary which has like just something inside which is turning, instead of you're using like a holo shaft, like. So yeah, but we changed a little bit. We still have some linear ones, but actually also there where we need again a lot of power and
compactness, because
compactness.
your wrist is, because when I was first looking at the wrist, I'm like, wait a minute, I don't see it. That's such a slender list. There's no way it moves in all directions. I had to get in really, really close to see how you did it. So that is the most compact, sleek wrist I have ever seen. And
Hmm.
I think there's also some very good design decisions on you looking at the range of motion and actually having a non-symmetric range of motion, because my hand can only go up so far this way, but it goes a lot further down that way.
Yeah.
And I noticed that you designed it the same way. And because of that, you were able to change the constraints on it so that, yeah, you can get that full movement in there. I wasn't sure you could get that. And then, like, sure enough, it's in there as well. So,
It is.
so
Yeah.
it's like, it is one of the most impressive ones. Now, one thing that I have to check on is that I think it was because it was a computer graphic image that was a head turner for me. Is I looked at it, looked like you had like a rotation below the knee. I don't think you do on the actual
No.
one, but it was kind of suggestive in that, and that's what they, okay, I gotta look at this and find out what's going on, because no one has any rotation underneath the knee.
No.
And
No.
of course your ankle joint is basically kind of like the wrist joint, which again
Exactly.
makes sense to some everyone. If they're not using a linear actuator, they're using a rotary actuator to do the same thing. That no one's really built them right in to the
Yeah.
ankle itself because it's too big. So that's pretty
We
interesting.
Well, on the ankle, we also do have like two actuators, like the wrist, like here
Yeah.
on the hand, or so, and you have like a middle point, and then you have two actuators where can just go in all sides, or like we do, but it's kind of limited in one direction.
Yes,
So
exactly. And same
and
same with the human hand, is that you can only do so
yeah,
much this way, but you get a
exactly,
lot that way. And that mechanism works the exact same way, which is why it's a
exactly.
perfect choice.
Yeah.
The other question I have about for anyone is, I notice it seems to be a lot taller than the other offerings that are out there. And is there any reason why you chose a particular height?
Yeah. I think that's probably I just want to have someone like the same height as me as me.
Yeah,
And so it's a little smaller than me, so it's one like in centimeters, like 180,
yeah,
and so I'm 183, so it's fine. But it's I would say it's more probably just try to do like build one like in a size of let's say the average in Germany. I would say that
that's what
was
I
for me.
assumed. It was, oh, it's a German demographic. That's the 50 percentile in Germany. Yeah,
So and mostly like all the machines are designed, let's say, in some ways, and like in the way to have like the average covered and whatever. And so and this is why also the size. And for us, it was also to do the proportion, like and bring the power in and all that. It is like the perfect size.
yeah.
If I make it smaller, I need to design it even smaller. Like, and yes, you will have less weight, but I think still the you will not save a much weight but you will have much less power. So it was more the decision in that way. So we tried different version. We actually also right now also discussed about internally if we just do two sizes because not so difficult to do it. But at this time we're coming out with one. I think it was already tough enough.
Yeah, and I guess that the question is how, whether you can reuse your training data that easily going between different sizes, different
Yeah,
embodiments. It seems that the fewer size, eventually everyone's going to get it. If you remember when the iPhone first came out, you could only get it in one color.
exactly. Yeah.
Same with like the Model T, right? So eventually it's just going to be one size. And then at some point, when we understand how scaling laws work with AI and the data collection, we have enough, then you can
Mhm.
start talking about mixing them up. But I agree, right now, the best thing is to stay with one size. Other questions, just like regarding your hand, if you could address it, uh, are you using tendons in the hands?
Mhm. Exactly. Like we have now a new hand coming up. So this the last hand was pretty limited. So it has 6 degrees of freedoms and whatever. It was too limited in our opinion. So we do have also, let's say, the sensor pads inside and whatever, but it was still too limited. And now we're coming up with a new one, still limited in my opinion. So it has like up to 16 degrees of freedoms, and we are working also already on one which we have, but it's not, in my opinion, not far enough to go to market because it's pretty complex. So this is like an hand where you can really start manipulating things much easier in your hand because this is a weak point about still in the robotic space, in my opinion. It's like the perfect hand, flexible enough, like a human hand, but in the same time still robust enough and really scalable and not too expensive.
Oh, okay. So I think on your first hand, you said it was 6 degrees of freedom.
Yeah, the first was 6 degrees of freedom.
Okay, and I want to make sure we get the definition of degrees of freedom right, because in engineering school, degrees of freedom, it basically meant like the number of actuators of control you had, and then there was like the number of joints. So,
Yeah, right. Yeah.
so it
Joints,
was
it has much more joints. Yeah,
that's what.
because
Okay, I just wanted to make sure is so
yeah,
that
yeah,
everyone is listening in isn't something like, oh,
exactly. Yeah,
how
you're right.
because I thought you say, wait a minute, I think there was more joints on there. It's just that the
Yeah,
degrees of control. So what that means is
yeah,
you got one motor and it makes
yeah,
all these joints turn
exactly,
at once. Okay, you don't have
exactly.
that control. So now you're
Yeah.
going to 16 degrees of freedom.
We could actually, let's say, now design just much smaller versions of it, so you can actually have like even, let's say, right now you're just closing like that, or so, because and in the future you could actually even do different kind of positions of your hands, because you are actually, let's say, have a motor like in every of this
Oh, okay, so you
axis.
can direct drive at the joints. Each IP
Exactly.
joint's going to
Yeah.
have one. So that
Yes.
means you won't be tendon controlled at that point.
Exactly. Yeah.
Oh wow, that's fascinating because
And
that's
there's right now even more coming, because like we also have a new invention, like where you can actually have here like an hexaput, like on your
yeah.
how do you call it, and Wurzel, your finger Wurzel. I
Yeah,
think maybe
it's
you
like
know
a
it.
root. The root of your
Yes,
yeah,
exactly.
the root cell is okay.
And there's a lot of things, let's say, in that space, but also here is all about like how do you make it like, okay, like make it complex since it's easy, but how can you make it like also reproducible, like also scalable and robust. This is also an really big topic, because at this time it's mostly even enough if you have like pretty good sensors in, and you have let's say 16 degrees of freedom is already pretty good. It's amazing,
Right,
like you
right,
can do a
right.
lot of manipulation
You can.
tasks with it. And
So
yeah.
so basically, what you're doing by putting those things in there, that means each one of your fingers is basically a little robot at that point.
Yes, exactly.
But whereas right now, the way to think of the fingers is that because you have the tendons that are going through there,
Yeah.
it's more like a backhoe, or a backhoe, or in German, what you call a bugger. that,
Yeah, yeah,
that you have like one central place, you pull on it, and like the whole
exactly.
mechanism kind of goes down through hydraulics. In this
Yeah.
case, it's doing it through the tendons, and that limits the control. Of course, humans, we have a hard time too. We can't control each one of our joints precisely. That's
Exactly.
you try to move one and the other one wants to go there. It takes a lot of
Yeah,
focus to get it to not do that.
exactly.
Some joints move in one direction, some move in multiple directions, like
Mhm.
your joints down here. Um, yeah.
Yeah, the hand is like super complicated, and it's also one of, let's say, one of the toughest things we built there. And I think even in humans, are I mean, the hand surgeons, I mean, they have the most toughest job. Like it's because it's so complex, and that's the same also for the robotics. Let's say in hand, it's super complex, and we make there always progress, but also in the same time, what is enough right now to just throw it on the market and be as robust as possible to actually
Yeah.
really solve
That's
issues today.
that's
So yeah.
that's the tricky part, is getting the dexterity and the robustness. So there are some very nice hands out there that can do a lot of things that are just not robust enough to last. A lot is because they're tendon driven, they wear out. The one thing I've always said, and it seems like this might be your focus, is that the business end of the humanoid is the hand. You've already kind of mentioned that before. That's the most important part. The idea of the arms and the legs is just to get the hand in the position it needs to be to do useful work.
Mhm.
And so you need to have a stable platform to be able to do it. But if you don't solve this, the rest of it, what's the point to it? So it seems like you're
Exactly.
putting a lot of focus in the hand, way more than I expected coming into this interview. And I think
Yeah.
that's very interesting,
Yeah.
that you're not just assuming that's a problem that will be solved or solved by someone else, but you're looking very, very closely at that.
Exactly. Because we want to solve it, or like we really want to solve it, because also like, if you're looking at our, let's say, physical AI, and also we just need to look at the human body, or like if like how do we distribute our compute, and how do which part is like in the hand itself, or like which is like a memory effect, like in your muscles or in your nerve system, like, so this is and that's why it's so important. And if we control that, in the same time, if we get it as close as possible on the human hand, it's much easier also to really use let's say the data even of humans, and at the same time closing the loop then with the robot, which having, let's say, enough sensors inside, but also degrees of freedom and all parts of your body.
And, and when it comes to training right now, are you using a lot of teleoperation?
We use basically all kind of methods. So teleoperation is one way. It's pretty good way, I would say. Why? Because simply like the robot, then you're not so much, let's say, the data is much cleaner and clearer because you're really doing with the robot, which and with all his let's say abilities and disabilities.
Yeah.
So that's why you get like both, like and this makes you strong. So you can have like one grasp, and you really it's a lot, it's enough, almost enough data than one like to really re-grasp it again and whatever. So and but we also do like methods like where we really watching humans like by example, for example. So we simply track the skeletons of a human as precise, as good as possible, and then actually watch how the human does, and then get all the data, let's say, out of that. But this requires again also, let's say, then more compute. So and then like and the other methods like out of simulation, out of let's say do a lot of simulation data, but this is really let's say for walking, for making like all kind of it's even the best and one of my our best methods because pretty good. But for really solving like as an assembly task or whatever, this is still, in my opinion, not good enough. and this is something we want to get, like let's say like that. We're working hard on it to get it better, because this is basically also the solution for a lot of issues, and you will save a lot of time for lifetime for that, your own lifetime to get a robot smart, but it's still limited. And this is also what lead us to redesign actually the whole robot, like in how many sensors we put in, and how do we like what kind of additional sensors we have to put in to actually close the loop from the virtual world to the to the real world.
Yeah.
This and this is also what I see a lot, like in the videos which are online. The most, in my opinion, are fake. Simple reason for that is I'm seeing like how many sensors they have inside and how they do. It's simply like from what they say from the virtual world. I don't believe, because there's not enough to close the loop.
Right. And all of those will have a place in there, but it doesn't seem like any one of them is enough. And I think the biggest problem with the teleoperation is that you just don't have the haptics. So the operator can kind of get the hand in position, and you can trigger some things to get the grasp, but it's not feeling the same. You're not getting that back.
Exactly.
And a lot of times you have to, when the object, if the bot is grabbing the ball, I'm always thinking, why isn't the teleoperator grabbing a ball as well? Instead, they're grabbing a virtual ball. Of course, their hands close down like that to try to persuade the robot to get in there. And you're just not getting that. And of course, if you try to do, like you say, that assembly task and simulation, it doesn't work because the physics is nowhere near accurate enough to be able to get all the material properties, everything that's going to be in there. That to me is it's like, that's the last speed bump you're going to give. All that other stuff is kind of nice, but it's becoming very, very hard to be able to get that quality data.
That's actually the good thing about AI, or like, because you do have already a pre-trained let's say a network which has already a lot of knowledge, which is collected like over a lot of time. And this is actually where, let's say, the requirement of really having exact same things like from the human or from the virtual world will get less and less, because you're basically closing the loop with the AI, or like and it gives you the right data, and this makes the robot, let's say, having this behavior like which is just almost free of failures, right? Yeah.
So yeah, I guess part of it is you're getting all these examples, like, what's the best way to grab a bottle? And you're
Mhm.
hoping the robot has some sort of semantic information that when it notices an object that's kind of bottle-like, it knows that this is the best grasping strategy because I've either been trained it, or, I mean, ideally, I've seen enough videos of people picking things up, and I know that this is how they prefer to grab a bottle, and not necessarily from the top. Uh,
Mhm.
And then the other thing is different strategies of types of bottles you could grab, whether it's a glass bottle or whether it's a
Mhm.
plastic bottle, a filled bottle or not, whether it kind of is able to see that ahead of time that, oh, I know what I'm going into. So I know what my expectations are when I go and grab something, and and what my motor torques and everything are going to be. And if it then surprises me that, whoa, wait a minute, that's an empty bottle. I was expecting it
Yeah.
to be a lot
Okay.
heavier, whether it then is able to adjust that. But I assume it's make you want it to kind of predict a little bit of what's about to happen in the next 5 to 10 seconds, and then play that thing through and then see if it plays out the way you want, and if not, make the adjustments. Is
Mhm.
that a reasonable assumption of what it may do in the future or what it's doing now?
Yeah, exactly. So like you just have to think about an bottle which is not see-through.
Right.
And how do a human react on it? So you just like you feel it by, like like in Germany you say like Scherkräfte, like the the forces which are
The
actually
shearing.
coming like
Yeah.
to yeah.
The sliding
So
forces. Yeah. Mhm.
and then you just grasp harder. Well, so what does it mean? And this is also not decided by your brain, by the way. This is actually again a compute part of your hand, and this is the interesting thing. And I think this one leads again to the architecture of physical AI. It's the most core, let's say, product we built. It's like how do you distribute your compute and which models you let's say like and how do you distribute them to actually have let's say and everything like timestamp like this. I don't want to tell anything, but everything,
Yeah.
anything is wrong, everything. But basically, like how the architecture, like our architecture is built, is very simply we only let's say divide the models, like the microservices, by actually by time. So to know actually in which part of your body they are in, and in the same time also which part is actually maybe required to be in a cloud, which part is actually in the main brain, and which part is actually in your nerve system. Right? So I'm talking about microservice like lane control. You cannot use that in your brain. Like the lane control is simply it's mostly in a microchip and it's very fast because of
Right.
the speed you're driving and whatever. So and that's exactly also for the robots the same. So you have a part distributed to like a compute to have like some functionalities which are fast enough to react, and that's how you cover actually even this kind of cases of okay the bottle is not empty or it is empty,
Yes. Right.
and that's how you actually react and send the right let's say and react already autonomously. So the hand has to have an own capabilities of reacting and manipulating in your hand without using the brain.
Okay, so basically what you're saying is that there's a type of like almost reflex action or
Mhm.
muscle memory, and that
Exactly.
one way you can do as a human is that if we're looking at the bottle, we can't see that there's water in there. We're not going to know that it's heavy.
Yeah.
So right now I'm kind of relying on my eyes, and I as I come over and I grab this, and if I'm assuming it's empty and it begins to slip, well, my eyes are going to notice it's slipping, so I'm going to grasp it harder.
Yeah,
But
exactly.
that's if I don't have any sensorium
Yeah,
in
exactly.
my hand. But now you've got where you're basically calling it the shear force that I go to grab it and suddenly I'm noticing that it's sliding because I'm feeling a sliding, and that tells me, oh, just push a little bit more. Don't
Exactly.
crunch the bottle, which could
Yeah.
be the overreaction, because that's a problem with a
Yes.
lot of control systems, is that when something starts to get unstable like that, it overreacts. And that was
Yes.
always a problem of, for the longest time, coming up with a gripper that could also pick up an egg was the hardest thing. To pick up an egg and it would break in no time. So that is a big control problem. There
Yeah.
is one other question, because you've been building actuators and you've seen a lot of the demos that are out there. There are many impressive demos. We've seen backflips and everything else, and then we hear kind of from behind the scenes like, yeah, but the robot really didn't last much longer after that because it was really having to
Mhm.
do a lot, putting a lot of stress on the system. From your own actuators, you're clearly looking at robustness and all the control. And I refer to this thing as the bot of Theseus. You're probably familiar with the ship of Theseus. And the idea is that if you're replacing the actuators in your bot like every month, at the end of the year, is it still the same bot? and and I'm assuming you're designing these things because I spent 8 years in Germany, so I know what German qualitate is like, and that things are supposed to be
Mhm.
robust and last. I'm assuming these things are built to last, and that your actuators, besides just having great performance as far as torque and everything else, you're really looking at reliability, durability, and lifetime.
Exactly. So actually, all of our robot arms are designed for 36,000 hours. So it means of lifetime. So they're like it means they're ready, and they reach that point, or like probably much more. So that's how a robust robot arm is designed. Now coming into humanoids, you will actually figure out that this robustness you need, like on a robot which is on a stable platform, is a different one, because if you're not getting like all the cases where you all the time, for example, hit against something or whatever. You basically never get hit. You're always like just moving your movements and whatever, and this is also why it's robust, and this is also what you guarantee as a company like ours. So but we had to be reinvent, like for example, in the robot arms, we are using also the gearbox of harmonic drive, or like it's
Right.
because it makes them, it's like with a flex spline. um it's compact, it's from the weight pretty good, and everything is like, it's a pretty good gearbox. So a lot of experience with that. But for the humanoid, we figured out this is not the right way to do. So, and this is pretty something what I saw that a lot of human robot companies are using it, but in my opinion, they're like it's not the right one. So it's so we had to redesign a complete new gearbox. One for sure, like we couldn't use like just a simple gearbox because like backlash is something every robot hates, and especially every person who has to control the robots. But and what we did, there's a complete new type of gearbox, which is compact, which is light,
Okay. So
which has a very, so, and this was the difference also from the humanoids. Even the last generation humanoid, which you saw also at the Gen 2 or Gen 1, both of them have our own gearbox, but we now made again a new step. That's also how we get it compact, how we get a lot of forces out of that space. But we and then and we are robust by falling, and not just that. So
yeah.
even if you're thinking about encoder technologies,
Mhm.
for example, what everyone the most are using, let's say, and let's say magnetical encoder inside. So if you look into like super precise robots, then you're more looking like for optical, but then you get like issues with dust and stuff like that. So, but and for the humanoid, you need robustness. This thing will fall all the time, and this will be also an issue. So we basically, what we did is like we invented a new generation of an inductive encoder where the distance and the angles are not so, it's like super robust, or so. And this is also how we get even the next step for a new encoder technology. And that's why it's so important to actually control all this, let's say, parts of your actuator, to actually be able to really react and build it, let's say, really a robot which can go into the field and is robust and still pretty good to control.
Oh, okay. Now, I'm assuming because the problem with the harmonic drives is that they're not back drivable, and you don't have a whole lot of torque transparency. So your new gearbox, you need to get rid of the backlash, which is what the whole point of
Mhm.
the harmonic drive. So I assume you have a certain amount of torque transparency and back drivability in there as well. And
Exactly.
then gearbox. So I'm assuming, okay, is it a planetary gearbox or is it something? Because you said it's something
Yeah.
different, something new,
Yeah, it's different. So planetary would be the easiest way, I would
right?
say, and I would say also the cheapest way. Or like and that, but we actually, let's say it's more cycloid what we use, but just changed and made it
Change
a
the
little bit
cycloidal.
different.
Okay, yeah.
Yeah.
So that's
So and
mhm,
this is what we basically like have right now, but because planetary simply has an issue with backlash. Right? So
yeah,
even if it would be easy to build and also a pretty good method, but the backlash is the issue.
yeah,
So you need more than one teeth actually in uh, the best is as many as possible to actually get and pretty, and then at the same time back drivable is also it's also not so easy then. So there's a method we now invented. So we did a lot, like we developed gearbox for a long time. So even like if you're looking into household robotics, has to be cheaper, because the most expensive component on your whole thing, it's like actually the gearbox. So we put a lot of effort into that, to build now 2 even different kind of gearboxes, which are pretty good and robust enough to go into the market. Yeah.
Oh, wow. So that's definitely exciting. Updates and stuff like that. I know we've gone down into maybe more technical details than we kind of expected at first. So
Mhm.
I want to thank you, David, for joining us today and giving you the background in Neura. Um, just to let you know, I will be coming to Automatica in München, so I
Awesome.
will be seeing you there as you
Awesome.
reveal the latest generation of For Anyone. And
Awesome.
next week, I also will be um, stopping by to see your team in Detroit at the Automate, which is the American version of Automatica.
Nice.
So I'll be getting my fill of industrial robots over the next month or so. And again, appreciate you taking the time to join us today. I know your time is very valuable. I think some very interesting insights, maybe a little bit different than you're used to speaking to other podcasters about.
Yes.
And there's big topics we couldn't talk about because we have to wait until the official release of the third generation of For
Yeah.
Anyone, and we will definitely follow up, probably live in Munich. So
Exactly.
yeah,
So also, you're always invited to just come by. So I could, like, personally, I could go much
okay,
deeper, and I could show you like the actuators, also the gearboxes, the sensor components. We
that's
did a lot of
I,
new cool stuff, and like every engineer loves to talk about this kind of
yeah,
stuff,
yeah,
and would love to show just everything. And like, it will also happen. So we will not just keep it for ourselves. That's never our aim. Like, also, if you look into all our robot arms, like, we cooperate. Like, four out of the top 10 robot players worldwide are selling Neura robots to the market, by the way. So and but nobody knows, and that's actually the way of how we go to market. And that's the same also here. We are not trying to just be the best and that's it. So no, we use almost an open source approach. So it's like supporting others for sure, kind of benefiting with them. That's why it's also about, but in the same time, we love to share.
yeah,
And this also, yeah, when you're coming by, like, come by, and I will show you like as deep as I can. And like, I would also love to hear your opinion, because I saw also even your first video, like some I don't know who sent it to me, like somebody sent it to me, and I really loved like the way of how you look at it, things. And I would love to share even deeper things to
I,
discuss with you
I
about
would
how
love to
you think about it,
hear it. Yeah,
because I think a second opinion is always a good thing, and or a third or a fourth. But I saw that you have a lot of knowledge. Yeah.
yeah, my career over the past 40 years has been looking at other people's robots and trying to figure out how to make a virtual version of them. So it's like
Oh,
just
awesome.
about every manufacturer. So that's why when I see these things, I'm just like instinctively, oh, how are they doing this and that? Because a lot of times they weren't sharing. I had to reverse
Yeah,
engineer
true.
and figure everything out. So I appreciate that. The other thing is I definitely have to come down there because I need a new suit jacket, and I understand that Hugo Boss outlet is center
Yeah.
is right down in that area as well. So
I need maybe one of the Neura t-shirts, or
oh yeah, that for sure. That for sure. But
hopefully.
definitely need to pick up on those things. Again, appreciate the time you've taken in this deep dive, um, and look forward to seeing you in what I think is like almost in a matter of weeks now. So it's
Yeah,
gonna be exciting.
some weeks coming very fast. It's already very
Yeah,
close.
yeah. Okay, so thank you very much. We'll probably close right on that. Yeah.
Good.
All right.
So,
So thank you
and
very much. It was enjoyable, and I look forward to an in-person meet.
same also here. So looking forward to meet you soon in person. And yeah, thanks for the
Yeah,
nice talk.
yeah, yeah. Tschüss.
Tschüss. Bye bye.